Hello. My name is Elliot Hoffman. I'm a software architect on the member portal team, and today I'm going to try to convince you that the plain text is a lie. The thesis of this talk is that there is no such thing as plain text. Some of you might be saying, I work with text files, or my source code is text, or I send text messages. And it's true that all those things are text, but they are not plain text. Plain denotes normal or default. And there's no such thing as either when it comes to how computers handle text. Computers handle text in a number of ways, and they're anything but plain and normal. So when you listen to this talk, I have three goals. The goals are that you will understand why text encodings and text handlings are important to your job. You'll have some best practices that you can use for your tool belt as you develop, design, and test software at Cerner. And you'll know a bit of background information as to how computers handle text so that you'll understand at a deeper level why you should do what I recommend. So let's start things off with the gallery of fail, or when text goes wrong by audience. First up, UX designers and web developers. You should care about this because your user interfaces and your web pages are the last mile of showing text to your users. This is a case of missing or wrong encoding used in a markup, in this case a web page, or JavaScript or something like that. This is the English language Wikipedia article on the word resumes, which normally has an E with an accent grave in two places there. You can see it's garbled up into two different letters. And this can happen if you use the wrong encoding in your website, your XML, or your JavaScript, or if you don't specify any encoding. Note that there's no error that happens here. There's no message letting the user know that something wrong has happened. It fails completely silently. This example is where the font that is being used to view a web page does not support the glyphs and symbols needed to render the content. This is the article on the city Tokyo, but it's being shown to you in Aramaic. And neither my web browser's fonts nor the fonts served by Wikipedia support Aramaic glyphs. You might think that this example is too contrived, so here is another example, which is more common, I think. 16th note used in sheet music, viewed on my Mac in Firefox, and again, instead of glyphs, you get that 4-digit number, which is sort of specifying I got nothing, so here's the designator of the symbol I wanted to show you, which of course is worthless to the user. So many valid characters are not supported by generic or default system fonts, and specialized web fonts might not support the characters you need. Next audience is API developers. So your APIs are responsible for specifying the data that you're delivering to your clients, and it's up to you to specify that correctly. Here's an example that I took from Wikipedia, and this is a fictitious API fetching the title of the Universal Declaration of Human Rights in Arabic. And what's happened is the client sent it with a certain encoding, the server sent it, the client read it, and as you can see, those things look a little different. And this kind of thing happens so often that there's a term for it called mojibake, which is a Japanese, I hope I'm pronouncing that right, it's a Japanese word, there's a Wikipedia article on it, it's very interesting. And this can happen when the server sends the wrong encoding with the data, or the client guesses and they guess wrong, or they guess on some default choice. Next audience is DBAs. You should care about this because your system stores and retrieves text. Here's an example of some data on a table. You can see there's a nice English key, but in this case, you get these diamond question marks, which are called replacement characters. Those got saved at the table level, which means that whatever data was in that string before is irrevocably lost. It can't come back, whatever that word is. And sometimes this can fail differently. Sometimes databases will simply omit characters they can't store. Sometimes they'll try to replace them with the closest match. Either way, you don't get the accurate data, and when you retrieve this and show it back to your user, they'll see question marks too. Last audience I've got is app developers. You should care about this because you don't want your system to crash when it encounters non-English text. We've all seen this before, and if you're developing internally, you may have seen this one, especially if you're Django. And the web app tried to decode text it couldn't handle and exploded. That's bad. Here's another example. Coincidentally, I was talking to a coworker of mine, Craig Gaskell, a couple days ago, and he mentioned he was having a problem with a test failing. And you can see, just look at that yellow part up there. Again, the file of his properties that he was testing was encoded one way, and his environment that was running unit tests expected another encoding. And as a result, the test was like, well, this logically is not the same thing. The test has failed. So source code, web pages, property files, all of these things have encodings, and every tool that you use to work with them, whether it's your shell, your terminal, or your printer, at some level, these things have to match up, and when they don't, you get these kind of failures. So we've seen a lot of failure. Hopefully you're asking yourself, how can I avoid this? And you have to ask yourself one question. Can I handle a pile of poo? So this is Unicode character 1F4A9, by the way, and look at that adorable smile. Pile of poo is a valid part, albeit weird, part of the Unicode standard. Unicode is a standard and system of storing and manipulating text to support thousands of languages in one system. Using Unicode in your system will help prevent a lot of the problems that we've seen here. And if you can store, transmit, send, and receive a pile of poo, then you're doing it right. But how do you handle this pile of poo? Before we go any further, I have to take a terminology break because the rest of what I'm going to say won't make a lot of sense unless we have some basic terms down. So, Unicode object. This is a data type that lets you handle Unicode text. For some systems, they use a different term, but the idea is the same. Java strings are Unicode objects effectively because they deal in Unicode. So it's the same concept. You encode and decode to and from what are called byte strings from it. So a byte string is just a sequence of ones and zeros that has no meaning in and of itself, but you can give it meaning if you understand the encoding. So the encoding is a mapping of what a sequence of things means. So you could say 0001 means A. So to encode is the act of taking a Unicode string and turning it into a byte string. The opposite, the inverse operation is decode, and that's to take a byte string and turn it into Unicode. Now, it can be tricky to keep the difference between encoding and decoding straight in your head. So one trick that I stole from Joel Spolsky's excellent article about Unicode is think of Unicode as the ideal state of being, which you want to be in all the time, and think of byte strings as weird, cryptic byte strings for computers or something. And that encoding takes the ideal state and weirds it up, and then decoding de-weirdifies it into something that you can work with in your system. So now that you've got the necessary terminology, let's begin text handling problem avoidance by making a sandwich, the Unicode sandwich. Credit for the Unicode sandwich analogy goes to Ned Batchelder for his pragmatic Unicode talk at PyCon 2012, but it was so good that I shamelessly steal it here. You can think of your system as divided into three parts. You've got two pieces of bread, the input and output layers of your system, and the middle business logic of your system is the meat. And you want to be dealing with Unicode in the middle, in the meat of your system, and you want to deal with input byte strings and output byte strings to exchange data with other systems or to store data or transmit data. Of course, good sandwiches are meaty, which means you want to maximize the areas of your code that you're working with Unicode. For example, you want to decode from byte strings into Unicode as early as possible after receiving data, perhaps right after receiving the response back from a web service call. Similarly, you want to encode from Unicode into a byte string at the last possible moment, such as the very last step before writing a file or making a database query. Working with Unicode inside your system will give your entire system a common ground that is reasonable and sane to manipulate text consistently. Now, you need to send and receive byte strings at some point, and so you have to choose an encoding. But not all encodings are created equal. Some encodings support only one language. Some encodings support several related languages, but not all of them. For example, German and French, but not Arabic. And you should never assume that the languages you speak or write in are the languages that your system will only ever encounter. So I say the best bread is UTF-8. UTF-8 is the best general purpose encoding for your byte strings. You'll learn more about why I think it's so good in a later part of this presentation, but for now, I recommend you choose UTF-8 for all of your byte strings, configure your choice of encoding explicitly. Do not rely on your parent process, your VM, the JVM, or your OS to dictate your encoding, because those settings might change over time or be misconfigured. You really should explicitly choose that in your system. And lastly, you should document this choice in both external-facing documentation, such as installation instructions or API docs, and your internal developer-facing documentation so that developers understand this choice. UTF-8 encoding supports all the text you'd ever want, but in this imperfect world, you will have to use encodings that are more limited. Maybe you're working with legacy systems, or there's some other constraint that prevents you from always working with UTF-8. In that case, what you need to do is test the critical points between the Unicode and the byte string regions. In other words, you want to test between the meat and the bread. Here's a handy table of how to test regions of your system when you're dealing with certain encodings. First scenario is when you're using an input encoding that does not support full Unicode. You want to test that non-English characters are faithfully decoded to Unicode. The reason English is a bad choice, so are Arabic numerals 0 through 9, is because many encodings have identical byte values for those symbols, and so it's a poor test choice. You won't get good results. You want to test things that are outside of ASCII characters. We'll get into what ASCII is a little bit later. Second scenario is that your output encoding does not support full Unicode. So again, you want to test that non-supported English character, or excuse me, non-English characters are faithfully decoded into Unicode. But the critical thing is you want to test how your system behaves correctly when you encode non-supported characters, because not everything in Unicode can fit into your encoding. What happens? Well, it's up to you. Do you want your system to raise an error? Do you want your system to replace the characters? Do you want your system to redirect the user to please ask for different characters? That choice is up to you, but you need to test it. And the last state is the ideal state, where you're using an encoding that supports full Unicode in both directions. And in that case, test it and eyeball it, non-English characters. You'll be cool. The Unicode sandwich analogy is useful for both new projects and legacy systems. If you have a new project you're developing, then it is worth your time to design with Unicode in mind from day one. You'll save yourself a ton of pain and suffering later. But even if you've got a legacy project that you're maintaining, I also say it's worth your time to audit from front to back how your system deals with text and see how compliant you are with the Unicode sandwich. So, with the practical stuff out of the way, I'd like to go into how computers handle text to give a bit of a background into why things are the way they are. We've talked about how to use Unicode and byte strings in your system, and you might be wondering why this is so painful. Why are there so many encodings? Why don't they all work together in perfect harmony? And I'm going to explain a little bit of history. Understanding this will help prevent errors in your system. And to make it a little more interesting than me just lecturing on the history, let's pretend that we are inventing the way that computers handle text from nothing. And to make this a little simpler, let's assume that we live in the United States and that we only speak English. Obviously, that's a very ignorant assumption with the state of modern software development, but it'll make things go faster. So we're going to start off, we have this challenge to invent how computers store and transmit text. And a good example to work off of is Morse code. Morse code's been around for hundreds of years, and it takes some symbols we want to represent and has a key and a value of some sequence we want to transmit, which is kind of what we're after. So that's a model for our approach. And we have to make some additions, and we have to make some tweaks to it to work with computers. The first change is going to be that rather than dots and dashes, of course, we'll use ones and zeros for binary because computers speak in binary. The second change is we want to make it easy. Let's use a consistent amount of ones and zeros for every symbol so that we know when one character ends and another begins. The next challenge is, what do we want to encode? To me, I think we want to encode capital letters, lowercase letters, numbers, all that stuff, and dollar signs, important to call out there, and some special things like I'm done transmitting a message, or make a new line, or ring a buzzer to let people know there's something coming. Those are called control characters. If we put all those together, we can fit those in 128 different slots. And we have just invented ASCII. If we do that, we can say, well, 128 is 2 to the 7. So we can just use 8-bit transmissions, ignore the last bit, or use it for error checking, and we're good to go. This is President Lyndon Johnson, who in 1968 mandated that all government computers support ASCII. So I hope that they since updated that, because that won't be good. ASCII is a great start, but it only works for American English. And so the obvious question is, well, what about other languages? And also, what about other places where English is used, but different symbols are required, such as in Great Britain, where the pound sterling is a legitimate currency symbol to be expected? Well, luckily, people typically deal with blocks of languages that are geographically or politically related. And when we get lucky, those languages share many of the same symbols. So one approach might be that we can create a group of standards that each standard maybe encompasses a block of languages, maybe a handful or a couple, and we'll just make one after the other. And there's a way we can do this if we start with languages that are similar to US English and work outward conceptually. What we can do is we can use that unused 8th bit from ASCII, and we can add that on, and the way binary works, we've just doubled the amount of symbols we can hold. So before, we could only hold 128 things. Now we can hold 256 things, which greatly increases what we can do. And one way to do this is we can use the first 128 slots as the same values we used in ASCII. So we'll just keep those around as is. But then for binary 128 through 255, we can take accent marks and special symbols and currency symbols and other letters that aren't in English, and we can put them in there. So there we have an U with an umlaut, E with accent grave, an S set, and that's great. So a bunch of countries in Western Europe use the same Latin alphabet plus these special diacritic marks and accent marks. And it turns out that we can support about 30 or so additional language with this, like Afrikaans, German, Swahili, and Icelandic, and others. And we have just invented a single byte encoding, although I think ASCII is technically also a single byte encoding. And every character is represented in exactly 1 byte. Here is what that might look like. This is a real-world single byte encoding that many of you have probably dealt with. This is Windows 1252, which is in fact a Western European single byte encoding. It's also similar to ISO 88591. Sometimes it's called Latin 1. As you can see, the lower values are ASCII, and then or the higher values, and when you go lower, you get extra symbols. So we can repeat this process. Let's do Arabic. Again, we take the first 128 characters from ASCII, and now we can fill up the remaining 128 with the Arabic alphabet and accent marks and things like that. Cool. Some languages, though, don't even fit in 256 slots. Simplified Chinese, for example. That's okay. We can just use more bytes. Maybe we choose to use 2 bytes per character, or 6, or maybe sometimes we choose to use 1 byte, and then when we run out, some characters use more bytes. Call those variable bit width encodings. So, or multi-byte encoding, excuse me. So, okay, we've got all these encodings. We can repeat this process over and over again for Russian, Greek, Chinese, whatever. Let's ratify them as international standards. So ISO 8859 is the standard that has done this for single byte encodings. There are other standards that are for multi-byte encodings, and we invented basically Western European, which is 8859.1, and Arabic, which is 8859.6. And if anyone uses these standards, they can communicate with each other no problem. So that's cool. These standards are only part of the story, though, because companies like IBM and Microsoft also decided to invent their own standards. Sometimes these are called code pages or OEM standards. And sometimes they map exactly to the international standard, like there's one-to-one. Sometimes they're just a little off to be annoying, and sometimes they're completely disparate. So here's an example of a symbol that's rather interesting. The euro symbol was added in 1996, I think, to the Windows 1252 encoding. So we're still making new symbols and having to add them into all these different encodings, which is something to keep in mind because we still have problems with the system that we've come up with so far. We have this glut of standards, and that's better than ASCII because now we can support different languages. But how do we intermix languages? What if I am a teacher in China who wants to teach Arabic and make a web page about it? How do I put those texts together on the same page? What if we run out of room in our encodings? We just saw an example where the euro symbol was added after a standard was already ratified. Do we just keep updating all the standards? Where do we put which standards accept which symbols? And there's no Rosetta Stone. We might write a way to convert between one standard and another, but with many systems supporting many different standards, it becomes complex to interact between all of them. So enter Unicode. So Unicode is one standard to rule them all. It attempts to be a single standard that supports thousands of languages. It addresses some of the limitations of byte string encodings and the things we've invented so far by operating at a level that's above simple byte representations of symbols. The foundation of Unicode is sort of this gigantic uber list of symbols called code points that were chosen by a vast multinational committee over a period of years and years. The code points are not concerned with the byte representations on the wire, what the symbols look like on the screen, or other encoding details like that. It's sort of a conceptual, just a big list. Here's an example of a code point in Unicode. At the top is a symbol that you guys are probably familiar with, and it's important to draw a distinction between what a symbol looks like and what a symbol conceptually is. So the symbol looks like this because that's a font on my computer that my computer used to draw it. But this idea of a lowercase a is what a code point is. You can see there's a key value for it, Latin small letter a, and this number at the bottom here, 0061, is the code point. It's an unambiguous way to refer to what's called a grapheme, which is a fancier, sort of higher level idea than a character. Here's an example of something from another language that I believe means east in Chinese and Japanese. And again, it's just a code point. It has a name in the standard, but the code point is the way that if I tell you about things, you'll know what I'm talking about. We don't have to worry about bytes. And even this is a code point. This is Unicode Snowman. Same thing. Snowman might look different if my font drew it differently, but at the end of the day, it's Unicode Snowman. Symbols like snowman, road signs, arrows, playing card suites are in Unicode. There's a lot of things. We have a virtually unlimited space to work with, though technically it's 1,114,112 symbols to work with. We can hold the world's active written languages, we can hold some historical languages, and we can hold miscellaneous symbols. In fact, there are places in those 1 million slots that are not even defined and are set aside for private use so that you and the people you communicate with can agree to use them for special uses. It's called the private use area. These have been used hilariously to store Klingon and Elvish. And it's, if you go to Facebook or something and flip it to Klingon, if you see Klingon glyphs, what's really happening is you're seeing Unicode private use symbols that your web browser's font supports. It's not official, but there's an unofficial official registry of things that people think is clever. They put it in there. So this is actually a private character. This is the Apple symbol. That's not an image. That is a single character of text that's blown up really big in font size, and it's private character F8FF, and it's just through sort of de facto agreement that my computer draws that in that font as an Apple symbol. So we need to devise, we have this cool high level thing, which is great, but we still need to devise a way to transmit it over the wire to other people so that other systems can process it. And we need to invent an encoding or talk about the encodings. We're not going to invent them. I'm just going to talk about them. And there's several encodings that we can pick from. First off, let me return back to UTF-8, the one I recommended earlier. And I'm going to give you a couple of reasons why UTF-8 is so awesome. The first reason, well, Unicode, to back up a second, is a variable with encoding. It transmits things in between 1 and 4 bytes, and it has some cool features. It's very popular. UTF-8 is used in Linux systems, and it's used as the dominant encoding of web pages since 2010, according to Google. So it's very widely used. And when I say according to Google, literally they wrote a paper on it. I don't mean like I Googled it and they said UTF-8. So second feature is simplicity. There's no need to transmit byte ordering information or care about the endianness of the processors or the parsers, or to say, hey, I'm going to send you 6 bytes just to let you know, and then when I'm done with those 6 bytes, that'll be when another thing will come. It's self-synchronizing, which means the bytes themselves take care of that. You don't need extra information in there. And the last cool thing is backwards compatibility, which is also a bit of a danger. So the first 128 slots of UTF-8 binary values are identical to ASCII, which means if you pass an ASCII file through something that's reading in UTF-8, it'll work the same just fine. But of course, the reverse is not true. You can't stuff everything of Unicode into ASCII, which again is why English and numbers and actually any ASCII character would be a bad choice to test your encoding and decoding. For historical purposes, there's UCS2, which you should not use because it's very old and busted. UCS2 is a fixed width 2-byte encoding, so every single symbol is exactly 2 bytes. And that worked really well with the original Unicode code point list until about the mid-90s, when they expanded the list of code points greatly, and we couldn't fit them in 2 bytes the way that they had devised the encoding. So UCS2 is deprecated in favor of the next thing I'm going to talk about, UTF-16, but you can still find it. The original implementation of the Java string class internally used UCS2. That's no longer the case. However, horrifyingly, Python 2 and 3, CPython, to this day, if you build it from source code, by default, internally uses UCS2, which means that you do not get full and proper Unicode support. Now, you can flip a flag, and a lot of packaging systems do this to get full Unicode support. And pre-Windows 2000 OS API calls would use it as well. However, UCS2 was deprecated in favor of UTF-16, which is fine to use. It adds support for those code points that cannot be represented in 2 bytes. And you can find it in a couple places. Since Windows 2000, Windows OS API uses it. The current Java string class uses it internally as the representation, so you get full Unicode support. The .NET environment uses it. And OS 10 and iOS's NS string type use it internally. Lastly, there's UTF-32. UTF-32 is a very straightforward approach. You can fit all the code points in 4-byte values, so why not just one-to-one map every code point to a 4-byte value of it and done? And that's what it is. And if you flip the right flag in Python, you will get full Unicode support by virtue of every Unicode object being represented in UTF-32. Of course, it's very large. So that's pretty much all I've got. We've seen how text handling can go wrong here. We've seen how to design and test systems with Unicode in mind. And finally, we've learned a little bit of history about text encodings. So there's a lot more on this topic. There's a lot out there on the internet. There's a lot for your personal system and for best practices in general. You should do more research on this. You should examine your system to see if you're using Unicode inside. You should examine your system to see if there's an opportunity for you to use UTF-8 instead of a legacy encoding. And finally, you should know that the plain text is a lie. Thank you. Any questions?
What's missing if you use UTF-8? Why would you use 16 instead of 8?
The question is, what's missing if you use UTF-8, and what are you missing if you use UTF-8 instead of UTF-16? So both encodings will represent all of the code points. The difference is going to be that you will have to specify byte ordering, or if not in your transmission, you'll have to say, I'm going to give you, like out of band, you'll have to say, like, I'm going to give you this data, but the most significant byte of the 2 bytes is first. That's one issue. Another issue is when you think about how much markup and source code is in ASCII characters, even though the language of the content might not be, then you're basically saying, well, every byte will be 2 bytes instead of maybe a lot of them can be 1 byte. They can be a smaller size. And I don't think UTF-16 has self-synchronization, though I could be wrong about that. I'm not quite sure about that. Anyone else? All right, cool. Thank you.